All right, so we're just going to go ahead and solve all the way out. We're going to solve an example problem using nodal analysis. So let's go ahead and do that. I'm going to go ahead and draw, how about I put a current source here and a resistor here. Okay, and then I will put ground right here. Go ahead and put a resistor here. And then I'll put a resistor here with a voltage source right there. All right, and so I can go ahead and use nodal analysis to solve this example problem, okay? So let's go ahead and label the nodes that we have with, I'll write some names for these nodes. How about that? Instead of coloring them, we'll call this one Vx, we'll call this one Vy, we'll call this one Vz, and of course we know that this node down here is ground, so I'm just not even going to label that. It's already got its little ground symbol. And let's give some values. Let's call this 1 milliamp of current. Let's make this a 6 volt voltage source, and then we'll just go with 1K resistors all the way around. All right, and so what we want to do is we want to solve for all the unknown voltages in the circuit. So we want to find Vx, we want to find Vy, Vz. And so basically, if we remember the first step from nodal analysis, it's to determine which of the node voltages are unknown. Okay, and so Vz, is it unknown? Probably, initially it is, but we look at it, we know that this side of the voltage source is 0. My source is rated for 6 volts, so Vz right off the bat is going to be 6 volts. Okay, Vy is clearly unknown. And then Vx, can we solve for the voltage there? We can't yet, so that's also unknown. Okay, but what we can do is we can solve for Vy using nodal analysis. And then once we get Vy, we already know the current that's going to flow through this resistor. And then using Vy, the current, and the 1K, we can simply use Ohm's law to find Vx. So let's go ahead and do that. So nodal analysis. All right, we identify that Vy is the node that we're interested in. So we're going to go ahead and next we're going to label all of our currents. So we figured out that there's already 1 milliamp on the left-hand side. So let's go ahead and label our other currents. We'll put one there and we'll put one here. We'll call this one I2 and we'll call this one I3. Okay. Now we need to make our little KCL equation for the node that we're interested in, which is Vy. So KCL tells me that the sum of the currents entering, which is 1 milliamp plus I2, is equal to the sum of the currents leaving. The current leaving is I3. And now what we want to do is we want to write the expressions. We want to write the expressions in this equation. We want to write the expressions, in this equation in terms of voltages and resistances, okay? So here we are. We know that the 1 milliamp is equal to Vx minus Vy over 1K, right? That's my voltage drop across my resistor divided by my resistance, plus I2, which is going to be 6 volts, minus Vy, right? I'm going this way, divided by 1K. And then I can set that equal to I3, which is going to be Vy minus 0 volts, divided by 1K. All right, so we've got our first expression here. Our second expression is going to come from Ohm's law, which we already know that Vx minus Vy over 1K is equal to 1 milliamp, right? There's no unknowns there. So we can just write, we could have really just left it to begin with. But if I say 1 milliamp plus 6 volts minus Vy over 1K is equal to Vy minus 0 volts over 1K, I can really get rid of the 0 volts there and just write Vy over 1K. And now I'm left with an expression that only has one unknown, right? I only have Vy as an unknown. And once I find Vy, like I said, I can use this expression here, that 1 milliamp is equal to Vx minus Vy over 1K, and then I can just solve for Vx. Okay, so let's go ahead and solve for Vy real quick. I'm going to go ahead and multiply both sides of this equation by 1K to get rid of all my fractions. So 1K times 1 milliamp gives me 1 volt. my 1K cancels here, so I get 6 volts minus Vy equals Vy. Okay, so I get 7 volts on this side, I get 2 Vy on this side, which means I get that Vy is equal to 3.5 volts. Okay, so I found, oh, I want it to be a nice little box. Vy is 3 volts, and like I said, I can use this other expression here, which is basically just Ohm's law, now to determine Vx. So I can, let me just zoom out over here, and I'll say Vx minus Vy over 1K is 1 milliamp. Multiply both sides by a 1K, so I get Vx minus Vy is equal to 1 volt. And I know Vy is 3.5 volts, so I get that Vx is 1 volt plus 3.5 volts, or Vx is equal to 4.5 volts. Oops. 4.5 volts. All right, so I have solved for Vx, Vy. I figured out Vz pretty early on, and we will be done with this problem. Went ahead and solved using nodal analysis. Obviously, we also used Ohm's law. That's not uncommon. That we would end up having to use several different techniques to solve a single circuit, but this is just one example of using nodal analysis to help us solve a problem. So with that, we're going to be done with nodal analysis for now, and we're going to move on to the next method, which I believe is superposition.